today we're going to finish our discussion about nuclear chemistry. So no questions over the previous stuff. So earlier I mentioned radio dating. So raise your hand if kinetics was your favorite chapter. All right, I thought kinetics was a good chapter. So here we see the word rates of radioactive decay, and calculations may be based on half-life. So the big exciting part of this is radioactive decay is a first-order process. What does that mean, first-order process? Yeah, that definition, probably that equation of a line that looks like log of concentration sometime down the road is equal to negative the rate constant times time plus natural log of the initial amount, right? Also, let me ask you a question. Is half-life constant for radioactive decay? Kind of. That's real committal, isn't it? Good, somebody's shaking their head no. First order processes, half-life is a constant. So here's this equation, and our property of log says the log of doing division, this would be equal to the log of NT minus log of natural log N0. Then we could take that to the other side and we'd get our equation of the line. So the rate of decay is called activity. We might think of disintegrations per unit time. If n sub 0 is the initial number of nuclei and n sub t is the number of nuclei at time t, then we have this equation which we could rearrange, and if I had more time I would have typed it out rearranged. There it is. We've used our property of logs, and this is the equation of the line. Here's our constant, here's our slope, here's our y value. So you can use this form or the form I just wrote on the whiteboard. So strontium 90 has a half-life of 28.8 years. If you have a 10-gram sample at time 0, t equals 0, then 5 grams is going to be present in 28.8 years. And if we go another 28.28 years, that would be 57.6, then we'd only have 2.5 grams. So one aspect of nuclear chemistry that might be a little easier than the chemical kinetics, we don't have to deal with molarity, it's just straight up mass. 10-gram sample, strontium 90, 28.8 years, we're going to have 5 grams. Wait around another 28.8 years, we're going to have 2.5 grams. Each isotope has a characteristic half-life. Half-lives are not affected by temperature, pressure, or chemical composition. So in the chemical kinetics, we saw, there's all these factors that affect rate. Temperature, physical state, catalyst. Half-lives are not affected by any of those things. It's a nuclear reaction happening inside the nucleus and can't really affect that. So of course, one of my favorite true and false questions is the decomposition of uranium can be sped up by oxidizing it to uranium +6 or something like that. Natural isotopes tend to have longer half-lives than synthetic ones. Kind of makes sense. If we find something naturally has radioactivity, it's probably been laying around for quite a while. So here's our uranium-238, 4.5 times 10 to the 9th years. Uranium-235, a little shorter. Notice these all decay by alpha, probably because of that larger than 82 atomic number. Of course, carbon-14 isn't so large, it needs to be undergo alpha K. So these lighter ones undergo beta decay. Hopefully you could predict that on some of the things we just talked about. Here are some synthetic radioisotopes. How do we get synthetic radioisotopes? Yeah, SLAM, exactly what we talked about last class. Nuclear transmutations, and that can be done in a particle accelerator or putting our sample right next to some other radioactive source. So, some interesting half-lives, years. Oh man, what is 0.022 years? I'm not in a Chem 1 mood. We could calculate that in seconds, but notice some of these, we'll see a slide later, sometimes you're given these at a hospital, and why they are radioactive, they take an image or do whatever they're going to do. So this should look familiar. This is natural log of 0.5. Actually, it's negative log of 0.5. So how do we detect radioactivity? Matter is ionized by radiation. That's what makes it dangerous. So there's this thing called a Geiger counter, and it uses that ionization to make electrical charge. So typically there's a thin window that the radiation goes right through, causes the ionization of a gas, and that's part of an electric circuit. The ionized gas can then carry a charge, current's produced, and the current pulses, and it's amplified. Kind of looks like electrochemistry. So to me, it kind of looks like a vacuum tube. And it is probably low pressure argon. Radiation hits this, causes this gas to be ionized, and we have ions. Kind of looks like an electrochemical cell. Ions conduct electricity through here, electrons through this. And here's some type of counter, counts events. Radio tracers, that's a real interesting concept for chemists trying to figure out chemical reaction. And a famous one is photosynthesis and carbon-14, trying to figure out the process. So chemists made some carbon-14, carbon dioxide, and then expose it to plants, and then isolate different compounds and see how the carbon, where it goes during photosynthesis. And I look at this thing and I think carbohydrate. So we say we used labeled carbon-14, and that helps us differentiate it from all the other carbon out there. And also in pharmacokinetics, there's this thing called the kinetic isotope effect. So if you break a hydrogen bond when your body metabolizes a drug, or when there's a physiological reaction, if you can replace that hydrogen with a deuterium, you make it heavier. And then if you can measure effect occurring, that's called the kinetic isotope effect. Also, a lot of pharmaceuticals, they have a drug and it works all right, but the body metabolizes it kind of fastly. A lot of times they'll say, well, hey, let's just take the hydrogen off and put a fluorine on it. And a lot of times that makes the drug last a lot longer in your body. So here's the exciting part. How do we get energy from nuclear power? Or why does a nuclear bomb release all this energy? So you might have heard of Einstein. Einstein came up with this theory that explained the photoelectric effect, and Planck used that. And here's another thing Einstein's famous for. Energy equals mass times the speed of light squared. So Einstein showed that mass and energy are proportional, where energy can be converted into mass or mass into energy. We probably see mass being converted into energy. I don't know if we really observe it going the other way, but we can imagine it anyway. And Einstein said imagination is more important than knowledge. Then, of course, there's the difference between knowledge and wisdom. Knowledge is realizing that tomatoes are a fruit. Wisdom is not putting tomatoes in a fruit salad. Oh, look at these neat thermodynamic terms. If a system loses mass, energy has to be given off. So we say it's I got all twisted up. Exothermic. If a system gains mass, it gains energy, then we say it's endothermic. So the speed of light in metric units is 8.99 times 10 to the 16th meters. This is all messed up. We'll see the speed of light. I'm going to just jump to the speed of light here. 3 times 10 to the 8th meters per second. Over here, it's already been squared. So it turns out a small change in mass causes a large change in energy. Mass and energy change in nuclear reactions are much greater than chemical reactions. So here's our good old uranium-238. It can alpha decay into thorium-234 and give us thorium. And if we could weigh out a mole of this, here's a mole of that, here's a mole of helium, and if you pull out your calculator, you're going to see that matter is not conserved. So here is the speed of light squared, and here's the mass difference. It gives us this many joule, and notice it's negative, so it's exothermic. So there's this thing called binding energy. The mass of a nucleus is less than the mass of their nucleon. Mass defect is the difference in mass between the nucleus and the mass of the nucleons. Binding energy is the energy required to separate a nucleus into its nucleons. And this equation here tells us the mass defect. So deuterium, that's an isotope of hydrogen, and it has a mass number of 2, where normal hydrogen has a mass number of 0, just has, a mass number of 1. Sum of protons and neutrons just has a proton, no neutron. Deuterium has a neutron. Tritium must have 2 neutrons. So a proton has a mass. So the other day I showed you that a neutron weighs a little bit more than a proton, because a neutron can like beta decay into a proton and give off an electron. That's how I like to think about it. All right, deuterium has a mass of that many atomic mass units. And if I sum these two up, we see that this is a smaller number than that one there. So where'd that mass go? That mass went into binding energy to hold those particles together in the nucleus. So if I take a difference between these, and I'm gonna just do it so I get a positive number, I'm not gonna worry about the sign. Now if we wanna use this equation, atomic mass units is not gonna help us. Bless you. 1 kilogram. This number looks kind of familiar. Well, when we put it in grams, we get pretty much Avogadro's number. 6.022 times 10 to the 23rd, but we're in kilograms, so it's off by 1,000. And then this is going to give us something like, now once I know that mass, I can plug it into this equation. Now I'll take my speed of light. I wrote down lots of digits, meters per second, and square that. And when you look at these units, you might think back about kinetic energy being equal to 1/2 mass times velocity squared. And what was the definition of a joule? A 2 kilogram mass moving at a meter per second. And so 1 joule had these crazy definition. So we get to sub this out. So there is the binding energy. And there might be some problems in the book where you're going to divide by the 2 nucleons. So there would be joules per nucleon. So here is a graph of binding energy per nucleon. We might see some interesting things. Here are some lighter elements, and there's this word called fusion here. Here's a heavy element, and we see the word fission and increased stability. So a heavier element can move towards a lighter, and a lighter element can move to a heavier. I didn't like that graph because we didn't have binding energy per nucleon. So let's talk about nuclear fusion first. What is nuclear fusion? The process of combining small nuclei together into larger ones. So here's hydrogen, here's deuterium, here's some weird isotope of helium. Here's that same helium isotope, 2 of those becoming our normal helium and a normal hydrogen. 2 normal hydrogens becoming deuterium and giving off a high energy electron. So it says here, the following reactions are believed to take place in the sun. What is the sun? Yeah, all this stuff. You can say the sun is a thermonuclear reaction. Does anybody ever wear Oakley sunglasses? Do you remember what they said on the side? Or they used to have a like trademark little thing. Oakley sunglasses, and it would say thermonuclear protection. And I was an undergrad with my physics friend, and he's like, oh, now I understand that. Why they print that on the sunglasses? The sun is a big thermonuclear reaction. It's giving off all this light, and you wear sunglasses. Now, nuclear fusion is kind of exciting because we imagine being able to harness it, and we wouldn't have all the nasty side effects of nuclear waste, these highly radioactive heavy elements that never go away because they have long half-lives. And so here is the energy released when this occurs. And so people are studying how to contain this in like a magnetic field and get these things stuck together. Your book also has some pictures of laser where they try and put deuterium in like a sample of deuterium and then hit it with a bunch of lasers from all different sides. and get this reaction to occur. And when this reaction occurs, you get this much energy. So isotopes in medicine, radioactive and stable isotopes have applications in science and medicine. And we just saw this with the carbon-14 being used as a tracer to figure out where in photosynthesis the plant takes the CO2 and where does that carbon ultimately go. So sodium-24, radioactive, you can put that in your blood, then take an image. Iodine and thyroid conditions. When you buy salt at the grocery store, what does it say on a lot of the bottles? Yeah, that it contains iodine. Before that, people would have thyroid conditions because you need iodine. I don't know what taking a lot of radioactive iodine is going to do. Somehow it just doesn't sound good to have all this radioactive stuff going off in your body producing an image. Now let's talk about nuclear fission. So here's our uranium-235. It's capable of a self-sustaining sequence of nuclear fission known as a nuclear chain reaction. So here is nucleus of uranium, and this is presumably a neutron. And when a neutron hits this, it was unstable to begin with, and it can break down into these daughter nucleides, and presumably giving off 3 more neutrons that can react with more uranium-235. Here are some other outcomes, and then each one of those are going to give off neutrons, and possibly you can see a chain reaction occurring. And so when these nuclei of uranium are close enough together, this is a little better picture than the other one. A neutron hits, this thing gives off 2, slams into these other uranium nuclei. They each give off 2, causing these to undergo a nuclear reaction, and you can see it accelerating. So how do you achieve critical mass? Supercritical mass. Here's subcritical mass. I'm going to give away all the nuclear secrets right now. Here's how you build a nuclear bomb. Enrich some uranium. Take all the 238 out of it and have some uranium-235, and you mill it out in such a way that you have another piece you mill out that they're going to fit together real nice and tightly. And so here's some normal chemical explosives, trinitrotoluene, and when this explodes, it slams these 2 pieces together and they get real close, and then that nuclear chain reaction occurs real fast. Now, I know your question in your mind is, what is a hydrogen bomb? A hydrogen bomb's where they have this nuclear fission bomb, but they pack it with a bunch of heavy water around it, a bunch of deuterium oxide. And then once the nuclear fission reaction occurs, it gives off so much energy that you get all that heavy water undergoes fusion. So then you have 2 nuclear events occurring. Yep. Well, first the fission happens, and then that causes some fusion to happen. So that's all we have time for nuclear chemistry.